Picking up where we left off the last time from Lewis Structures Part 1, Tips and Tricks, those invaluable tips and tricks I gave you, we're now going to learn how to calculate formal charge, which is an important topic for you to master and one that I have found traditionally gives students a bit of difficulty. However, if you follow what I hope to be these very clear instructions here, you are going to master this as if you were breaking matchsticks. So, 3 steps and you will arrive at the answer you need. However, I would like to illustrate this in the context of an actual structure first. So I'm going to come up with a Lewis structure that I know has formal charge. Carbon monoxide has formal charge. I'm not going to go through developing the Lewis structure for this. It's actually a little bit of a tricky one, but this is how it looks. So now we can focus our attention on calculating formal charge for each individual atom. And that's one thing you should realize right away. When we talk about formal charge, we're going atom by atom within the structure. So we want in step 1 to take the total number of valence electrons for just that atom. In the case of carbon, we know that to be 4. In the case of oxygen, we know that to be 6. Now, in order to get at formal charge, we take that number of valence electrons, which is 4, and then in step 2, we subtract all the non-bonding electrons that we assign to carbon, which in this case is 2, right? We have a lone pair there. So that's going to be minus 2. Notice carbon is making 3 bonds to oxygen. So the next thing we want to subtract is 1/2 of those 3 bonds, those 3 bonding pairs. So 3 bonds is 6 electrons. We're going to take 1/2 of 6. Okay. What does this give us mathematically? Well, 4 minus 2 minus 3 equals -1. So we can assign a formal charge to carbon of -1. What about oxygen? Rinse and repeat, right? Notice we have 6 valence electrons and again a single lone pair, so that's 2 electrons. And again, oxygen has 3 bonds too. So it's going to be the same thing all over again. Minus 1/2 of 6. 3 bonds have 6 electrons. And interestingly, this time, 6 minus 2 minus 3 is going to give us a charge of +1. So we can assign a charge of +1 to our oxygen. And that's really all there is to it. Notice in this little formula here, they have you adding these 2 things together and subtracting them from the total valence electrons. But that's the negative of the 1/2 bound electrons. You're basically subtracting all the way through is what I'm trying to explain to you. So that's it. You've done it. It's not really so bad. Now notice that carbon monoxide is a neutral molecule. There is no charge on carbon monoxide. So it is important, in fact, that these 2 charges, the -1 and the +1, are canceling one another out to give us back this neutral molecule. Now we're going to look at polyatomic ions where this is not the case, because polyatomic ions typically have a charge, right? So let's now move on to considering that situation. We already dispensed with carbon monoxide, so now let's turn our attention to polyatomic ions, and we're going to start with the carbonate ion. So the carbonate ion, one thing I want to bring to your attention is when you have a negative charge, you have to add electrons to your valence electron total. So in other words, 4 valence electrons for carbon plus 3 times 6 valence electrons for oxygen, now plus 2 electrons that represent this -2 charge. So you must do that in order to get a correct number. That's going to give us 4 plus 18 plus 2, 24 electrons that have to go into our Lewis structure. Let's do the usual order of business. We're going to do our skeletal structure. We're going to make some bonds. We're going to distribute some electrons until we get to 24. Almost there. Okay, if we count that up, I'm pretty sure it's going to be 24 electrons. Now, we have a problem. Carbon doesn't have an octet. We don't like that. So we're going to take a pair of electrons from any one of these oxygens, actually, and we're going to move it to make a double bond. And then we're going to end up with a structure that looks like this. It is going to be a valid Lewis structure. But we know this molecule has a charge of -2. So there's something else we have to do. We have to put brackets around this molecule and indicate that it has an overall charge of -2. This is an important step. The question is, where is this -2 charge coming from? And guess what? It's coming from formal charge on some of these atoms. So the detective work you have to do here is which atoms are supplying the formal charge. So let's go from left to right here and figure it out. And we're going to use that formula we just used a minute ago, which is, we're going to look at this oxygen atom here, and we're going to say, okay, it has 6 valence electrons. I see that it has 3 lone pairs, so I'm going to subtract all of those. And I'm going to take 1/2 of the bonding electrons. There's only one single bond, so that's going to be 1/2 of 2, which is of course 1. And when I do the math here, I'm going to find out that the formal charge on this oxygen is -1. So I can even write that here. I can write a little -1 here. Now, we could repeat this process for this oxygen, but you can see that it's exactly the same as the oxygen we just did. So it must have a charge of -1 too. What about the carbon? Well, the carbon has, so these were our first 2 oxygens right here. Now we're going to tackle the carbon, 4 valence electrons, and it has no lone pairs, and it has 4 bonds around it. So 4 bonds is 8 electrons, minus 1/2 of 8 is 4. No formal charge on carbon. How nice. What about this other oxygen over here? Well, let's do it again. 6 minus, now there's only 2 lone pairs on this oxygen, so that's 4 electrons, minus 1/2 these electrons in the 2 bonds. That's 1/2 of 4. So we have 6 minus 4 minus 2 equals 0. So 0 formal charge on this carbon, 0 formal charge on this oxygen. Guess what? The 2 -1s on these 2 oxygens here do in fact add up to this overall charge of -2. Now I want to make another interesting point for you. I'm going to rewrite this one more time. Remember how I said oxygen likes to make 2 bonds in general and then have 2 lone pairs? Well, that's true, but I said, what if we have formal charge? So notice in this case, oxygen actually has 3 lone pairs around it and is making a single bond and is assuming a formal charge of -1. So this is an example of how things change in terms of the way an atom of an element might bond, how many bonds it has, and how many lone pairs it has, depending on whether or not it has formal charge. Now, another way I like to think about this, I gave you a formula, right? And I said, you know, you take the valence electrons, you subtract the lone pair electrons, and you subtract 1/2 of the bonding electrons. Very nice. I think an illustrative shortcut is this. What if I were to imaginarily break this bond between carbon and oxygen in half, and I were to tell you that one of these electrons belongs to carbon, and the other electron, see how things are being shared, we can say belongs to oxygen. That's where those electrons originated in the first place to make the bond, right? So at this point, we could simply say, okay, 1, 2 electrons here, 3, 4 electrons here, 5, 6 electrons here, plus one more from this shared bond, that's 7 electrons. Oxygen, we know, only has 6 valence electrons. So this is for you conceptually to realize why oxygen assumes a negative charge in this case. And we could do the same thing over here where it doesn't have a formal charge. We split both of these bonds in half. That means from each of these bonds, one electron we can think of as being assigned to the oxygen. That means 1, 2, then 3, 4, 5, 6 for the lone pairs, 6 electrons, 6 electrons, meaning the valence electrons that oxygen has and the number of electrons we actually assign to it in the structure. Now, I'm going to let you tackle these two. I want to make one point, which is if you have a positive charge, as you do in the ammonium ion, you actually take away an electron. So that when you're counting up your electrons, remember it's one less than if it were just NH4 and not NH4 plus. NO3 minus, the minus should technically be up here, is going to have one additional electron. So test your metal on doing this. Don't let formal charge defeat you. It is really not that bad. I threatened one more thing before we part company, however. I threatened you with talking about resonance in this short video as well. So let's talk about the resonance of the carbonate ion. How many structures do we think, resonance structures do we think it has? I'm not going to bother. I'm going to be lazy and I'm not going to well, I really should. I'm going to draw the lone pairs as bars because just make my life easier here. And another one. And another one, which is blank right now, but that won't last. So resonance means we're really just moving this double bond around. And we have to write all the possible resonance structures here. For this particular polyatomic ion, it's going to be 3, right? And in each case, of course, these are going to have a charge of -2. So that's a little bit messy, but I think you get the idea. And you draw these double arrows between each of them. I remind you, as I told you in lecture, this is a somewhat artificial construct. Each of these bonds between carbon and oxygen has something that we call partial double bond character. But in terms of drawing them, you go this route. Okay, that's it. Hope that was helpful. Hope you're gonna just dominate formal charge and resonance structures. They're important.